Welcome student to this episode where today we will talk about Tychonoff's theorem for finite products, and exactly we will talk about what is called the Tychonoff theorem for two spaces x and y. Both of them will be compact, and we are wondering what happened to the product topological space. Is it going to be compact or not? Of course, this theorem has generalization to a countable product of spaces as well as arbitrary product of spaces, as we will see later. So we have this theorem here, which is a very simple statement. As expected, we have two spaces, both of them are compact spaces, and then the product is going to be a compact space. And the proof we will give in here is a little bit technical, so I advise you to pause and play the video, try to think about each step in the proof so you can understand everything up together. So here, as usual, we will start by assuming my two spaces x and y are both compact. So here we have a compact space, so any open covering for x will give me a finite subcover, as well as any covering for y will give me a finite subcover. And we want to show that the product is a compact, so I will take an open covering OI on the product topology. Now, the first thing we notice that for any point x and x, y and y, there exists an open set. Usually I will call it v of x comma y, w of x comma y, such that, of course, x will belonging to vxy, as well as the point y will belonging to wxy, and this of course will be in OI. I mean, if we go back to the product topology, we said that the open set in the product topology usually of the form open set in x with open set in y. So just let me emphasize here, this is open in x and this is open in y. So usually this is how the open set looks like in the product topology, or at least a union of those. In any case, it will be subset of OI because OI is already an open set. So those are the bases and they must be inside an open set. Now, this will help me to keep my focus here in this part, because this is open, this is open. We'll see that this is a very good thing, because now, let me just also write it down. So it suffices to find as finite subcovering for these sets Vx cross Wxy. And instead of finding finite subcover for the OI, we will just focus on those, trying to find a finite subcovering for the V's and the W's. So that's what we'll do next. Now, next step, what we are going to do, we will fix a specific x. So let x0 in x be a fixed point, be a fixed element. And I want you to look at this set here. If we look at this set, x0 as a point cross the y, which is usually we call it the tube or the line. If we just think about what happened in the real number, if this is x0, this is the line, this one, which is, in a way, it's another copy of y, and we already proved that before. So this is just homeomorphic into y, which is, by the way, same. It's just homeomorphic to Y, which is compact. Okay, so what do we get? What do we gain from this? We gain the following. Remember or recall that v x naught comma y cross w x naught comma y is an open covering for this space, which is the specifically with x0, which is compact. Hence, it has a finite subcovering, because any compact set has a finite subcovering. Let me just give it a name. I'll call it with a different color here, maybe this one. I'll just call it Vx0 y1 cross Wx0 y1. The next one is same, x0 y2 cross Wx0 y2. And because it is finite, we have to stop at somewhere yn with Wx0 yn. So the idea is I only focus on this space, which is compact. I already cover it by x0, x0, and I get a finite subcover, something like this one. So please pause the video, watch it again, because now what we will do next is the whole idea of this proof. Now, set Vx0, I want only this set to be the intersection of all those V's. So I will take the first V, I intersected with the second V. Of course, all of them will have x0, because in each V, it has x0, that's for sure. Vx0, y, which is, of course, open set in X containing x0. Why it is open? Because each one of these V's is open, and this is a finite intersection of open set, so it must be an open. Now, if we look at this one, we can reach to a very good conclusion, which is the following. If we take this set and we take the product with y, this one is contained in the union of finite number of sets of the form Vxy, Vx0y, Wx0y. So the idea is like mostly like the induction, if we think about it. First of all, we prove that if we take y with a product with only a singleton, this can be written as a finite union of v's and w's. Next, if we take all the intersection of those v's, and then we take the product with y, again it will be in the union of those sets. Again, finite union of those sets, because it's just the intersection. You can try it, take the intersection. So here will be cos y, cos y, cos y, and so on, which is for sure will be just a finite intersection of those. Now we reach the final, almost the final step. Let me just write it down here in red. So to show that x cross y is compact, it suffices to show x cross y is contained in a finite union of the spaces Vx cross y. So the idea is, what we will do is, let me write it down here. What we want to prove is x cross y is equal to, or it's a subset of finite union of Vx cross y. Now, why this is enough for me? Because it is finite union. Each Vx cross y is a finite, as we just said here, it is a finite union of V's and W's based on this. And so we'll get finite union of this one. This one is already a finite union of V's cross W's, which is exactly what we want to prove as a compactness approach. Okay, how we are going to do this one? This is of course very, very easy, and we did this so many times so far. So what we will do is, we'll just write x cross y. This is subset of all x and x, the union of x cross y. I'm sorry, we'll take this one, please. X. Now, because x is compact, since x is compact, here I would take only finite subcover. So this will be just a finite union. Just let me do it that way. So from j equal 1 to m, Vxj cross y, which is exactly a finite union of Vx with y. Now each one of these is already a finite union of V's cross W's. So this is will be a compact. Hence x cross y is compact. And that's the end of the proof, and that's the proof for Tychonoff theorem. Follow-up note: by an easy mathematical induction, by applying the mathematical induction principle, if xi, ti is compact spaces, for I equal 1 to n, then the usual product, the finite product, will be also compact. Is a compact. And that's exactly what we need here. Thank you very much for watching. Please